Have you ever wondered how power transformers, one of these things, really works? Well, that's what we're going to look at today. These are all power transformers, from the really small ones that are probably around 60 watts to the bigger ones that are 180 watts or so to 500 watts to a kilowatt. And of course, there are even bigger ones like the ones you see on the sides of power poles, or the gigantic ones at power stations like the Hoover Dam. What we're going to do today is take a look at one transformer, namely this one, and investigate it and use that to figure out how power transformers really work. And when I say really work, I mean more in depth than simply it's the number of turns going in to the number of turns going out that sets the voltage. Well, with all of that said and done, let's get started. So, to investigate this transformer, I've set up a little circuit here, and it is a bit of a can of worms, so I'll quickly explain it. The transformer has two outputs or secondaries, 30 volts apiece, and you can either put them in parallel or series to get 60 volts. We're not going to use them right now, so I've just insulated the ends with MAR connectors. These are the primaries for the transformer, and once again it is actually two coils. It is one coil at 120 volts and another coil at 120 volts. And I have them in parallel because our input will be maximum about 120 volts, but you could put them in series if you were in another continent like Europe or Africa or Asia and needed 240 volts as an input. So for now, just pretend that we have a single primary of 120 volts, and I've set up this voltmeter so we can look at the input voltage, the RMS voltage. And I've also set up the oscilloscope so that it's showing us the voltage going in, its waveform. And I have a 10 ohm resistor in series with the primary winding, and I'm using that so that the oscilloscope can show us the instantaneous current. And what that amounts to is, if I start cranking up the voltage, we can actually see both voltage and current going in. This trace is the voltage. This trace is the current. And to put things in perspective, each one of the divisions on the scope is about 100 volts. And similarly, each one of the divisions on the scope for current is about 10 milliamps. So you can see that we have a relatively low current. Now, the interesting thing is, if I increase the current a bit, you can see it a bit better. You can see that the current, this one over here, is lagging or delayed somewhat from the voltage. And that's a very typical characteristic of a coil, or more formally an inductor, which is just a coil either around a metal core or in free air. Now, what we can do is crank up the voltage some more. We're now at about 80 volts. That's pretty low for this transformer. And, well, everything rises as you would expect. But now, what you'll notice is as the current rises, it starts to get weirder and weirder to the point where we now get quite a horrible peak over here. And if we crank up the voltage now going higher, considerably higher than our 120 volts that we would like, that peak gets worse and worse and worse. And what that means is there's quite a spike of current going in. In fact, maybe what I'll do is I'm going to just reduce the scale so we can see it a bit better. And, well, I guess that's as far as I can crank up the voltage, but there certainly is a funny spike occurring over here, and that is because at these higher voltages we need much more current to energize the coil because the core goes into saturation. And to understand what's happening, what we need to do is take a look at the so-called BH curve of the iron in the core. So to see what's happening, we can go right back to Maxwell's original equations, which are this and this. And they might look a bit horrendous, but all this equation really says is the electric field in a loop, one turn around the magnetic core, is somehow related to the changing flux density, the B field, in that core. So we can say the voltage we see is some way proportional to the B field. And we have a graph here that shows the properties of the steel core, and it shows us the B field on this axis, and that B field is in Teslas, and it relates it to the magnetic force field H on this axis, which is very simply almost directly related to the current running in the wires around our core. And what happens when we apply a voltage is we have a voltage, or really it's the derivative of the B field, but we'll just say it's the voltage, and that voltage is going up and down for all intents and purposes here, and this graph maps that to the required H field going up and down, and that H field gets mapped to current. Now look what happens when our voltage gets so high that we need swings in the B field that go all the way to the top of this graph. Well, they hit this point, the saturation point, and now suddenly to keep going up we start needing huge amounts of current, and those huge amounts of current are the spike we were seeing. So that's the basic cause of those spikes, and that's also what essentially limits how much voltage you can put on a transformer. I mean, that's assuming the insulation doesn't break down or anything like that. And when you reduce it all, you can really get a couple of kind of simple equations that describe the operation. The output voltage of a transformer in RMS, the type of voltage we normally see on voltmeters, is a little over 4 times the frequency times the number of turns times the area of the core and the peak of the B field. And the reason we talk about the peak of the B field is transformers are typically designed so the peak does not really go much above this point, and we don't get those horrible huge spikes in currents going in. So that's what governs the output voltage. It's essentially equivalent to however big that B field is and whatever the area of the core is and the number of turns in the coil. The current that's going into the transformer, well, again, is really just related to the H field over here. We have a square root that converts peaks to RMS, and we have an N over here that takes into account the number of turns and loops in the transformer. And to make things a bit more complicated, this is actually the loop length through the magnetic core, which is generally just an estimate. Normally, we don't even worry about that. We just say the H field is roughly in some way proportional to the current, and if we wanted to know for sure, we'd actually measure it. Anyway, enough theory. Let's do a little bit more experimentation. So if we look at this again, what's essentially happening is we apply a certain voltage to the primary, and for that voltage to be countered by a voltage generated in the core, we need to draw an appropriate amount of current, and the current we draw is the current we see on the slightly lagging trace. And again, as we increase the voltage, because of saturation, at certain points in the curve we have to draw an absolutely huge amount of current. Now in this case it's only maybe 10, 20, 30 milliamps, but you can imagine that in a bigger transformer this might start to be a problem, or if we move it even further into saturation. Now let's get back to a much nicer zone, and you can actually see the interesting thing is if we set the voltage to about 118, 119 volts, the transformer was clearly designed so there was a little bit of a peak here, and it's not because they particularly wanted that peak, it's because they made a bit of a compromise in terms of the size of core, the number of windings, and so forth. And because this is really only somewhere in the 15 milliamp range, that peak doesn't really matter. But if you had a lot of transformers like this, it would be a little bit hard on the power system. All right, getting down to a more perfect type waveform where we have essentially a sinusoid going in, and interestingly enough, the voltage from my house, this one here, seems to have a flattened top, so something funny is going on in the power distribution system, but that doesn't really matter for what we're doing. Now the question I have for you is, if I were to disconnect one of these primary windings, would the current flowing into the transformer change at all? That's the quiz. You have a couple of seconds to answer. Okay, let's find out. And if I've done things right, I can just pull off this connection and look, it did not change. If I put this back, you can't really see the difference. And the reason it did not change is because what matters is the total current flowing through the core, and whether that total current is split between two windings or one winding doesn't really make any difference. So that's probably the first maybe unexpected result, but let's continue on. Now it is worth pointing out that again the lagging current makes the coils in the transformer look like an inductor, which is a separate type of electrical device, a very common circuit element. For our purposes, we just want to make sure that the inductance is big enough so that this current is relatively small, and when there's no load being drawn from the transformer, we're not drawing a lot of current from the electrical system, which would be, well, it wouldn't be consuming any power, believe it or not, but it would be consuming current, which does load transformers up the power line. And you'll notice I said something very funny. I said it's not consuming any power even though there's current flowing, and that's because the two waveforms, the current and the voltage, are actually separated by 90 degrees. And what that means is during part of the cycle, and it might be kind of hard to see here, you have the two currents, well, over here, multiplying together when they're both positive to be a positive value, but then at other parts of the cycle where one is positive and the other is negative, they're multiplying together to be a negative value. and current multiplied by voltage is power. So what you have is during part of the cycle you have power flowing into the core, and during the other part of the cycle you have power flowing out of the core. So when you have this so-called reactive current going into the transformer, what's essentially happening is during each cycle the power is going in, it's getting stored in the magnetic field, and then it's coming out of the transformer again. And so that's called reactive power or reactive current. And it's just something we have to live with and try and minimize, because it doesn't really do any good other than magnetizing the core. That is really just an inductor. What's of course more interesting to us is to use this thing as a transformer. And we can do that by starting to look at some of the voltage outputs. Okay, so what I've done is I have turned off the power because I'm going to touch a few terminals, and I want to make sure that I'm around so you can see future videos. And anyway, I'm going to attach a light bulb, or a socket with a light bulb, to our second primary winding, making it now a secondary. In other words, we'll just use it as an output because, well, in many cases, unless transformers are wound in a very specific way, it doesn't really matter what's a primary and what's a secondary. So now we have a load, and maybe I will unscrew the light bulb a bit so it's turned off, and well, we'll just rest it here. How does that work? That's good. And the other thing what I want to do is set up this voltmeter, and I've actually got it on a set range. And what we're going to do is maybe we will add a loop with this yellow wire with alligator clips through our coil. And the reason we're going to do that is, if you remember Faraday's equation, which tells us that the voltage for a loop around a core with changing magnetic field, the voltage in that loop is proportional to the value of that field. So we're going to use this as a way of looking at what the value of that changing magnetic field is in the core, particularly when we load it and when we unload it. So now that I've said all of that, let's try turning on the power. And what are we at? We're at 92 volts. Why don't we'll make it just a little bit less so that we have nice looking waveforms there. And what do we have over here? We have about 0.159 or 0.16 volts across our loop. I suppose we could be daring and try and get it up to maybe 0.2 volts. Will we get it to that without getting too horrendous a current? Yeah, we'll make it 0.2 volts over here so that it's just a little bit more obvious. And now, my question to you is, what do you think is going to happen to this current and this voltage when I screw in the light bulb? There's one way to find out. Well, that current went through the roof, and this voltage went down a bit, but not very much. Well, one of the reasons it went down a bit is because I have a 10 ohm resistor in here that is now probably getting about an amp or so being drawn through it, and it's dissipating about 10 watts of heat, and it's dropping the voltage by about 10 volts. So what I'm going to do is very quickly change the setup so I have a 1 ohm resistor in series, which will be more appropriate for looking at the bigger currents. Okay, so through the magic of cables with banana plugs, I now have the scope's current channel connected to my custom box here that has a 1 ohm resistor in series with the AC line. So what that 1 ohm resistor does is for every volt across the resistor, we see it means there's 1 amp flowing through the wires. So with all that said and done, let's turn the power back on, and right now you can see that there is hardly any current flowing. Well, there is that roughly 10 milliamps that we saw before, but now on this scale, well, it's virtually nothing. And I've just actually changed the scale here to 1 volt per division, so that means that each division represents exactly 1 amp. Now that we're set up to look at slightly larger currents, let's see what happens when we screw in the light bulb. We've got about 104 volts going into our core, and our 1 loop flux measuring turn is showing exactly 0.2 volts. So we'll turn this in. Can I do this so you can watch the current or watch the voltage? Yes, look at that. So the voltage here has hardly changed. It's gone down a bit. And the question is, why did it go down a bit? Well, it went down a bit because the voltage on the input went down just a little bit, and it went down just a little bit because of all the resistances in the wire, in the coils, in the wire going to my circuit breaker panel, and so forth. So there you have it. The other thing that is worth noting is the current, and maybe I will just increase its scale a bit, now almost perfectly follows the voltage. And if I adjust it a little bit more carefully, it probably will, scope isn't the best. If I can adjust it just right, well, there you go. They match up exactly. And so what that's showing us is now the current that this light bulb is drawing is so much greater than the magnetization current that, in fact, the only current that we're really even noticing going into the transformer core is essentially the current that is supplying the power to the light bulb. And again, looking at this, we have about the same voltage on this coil, which means the flux in the transformer core has really not changed. And interestingly enough, on the electrical version of Stack Exchange and a number of other places, there were some vehement discussions that I saw where people were insisting that when you drew more power through the core of a transformer, you would in fact be increasing the flux in the core. Well, that is 100% wrong, and we've just proven it. So what's happening with this magical situation? How does the primary know that the secondary is in fact drawing more power, and that it should in fact have more current flowing into the transformer? Well, here's what happens. When we turn on the light bulb, a current now flows through the secondary. And if you recall, the current flowing in a coil around the core generates an H field, a magnetic force field. Well, that magnetic force field is opposing the magnetic force field that is created by the current going in the primary. That opposing H field is now making the H field that the original magnetization current was providing not big enough to generate an equal voltage to what the mains is supplying. So what happens? Well, more current has to flow in the primary wires and the primary coil to increase the H field to make sure that the flux in the core remains at its original value. And so that's what happens. The bottom line is the system works very nicely. When we draw current here, we draw current going into the transformer. Now, right now, this transformer is just acting like an isolation transformer. Voltage in, voltage out is the same. But if we changed the number of turns on the core, on the primary or the secondary, we now get a change in voltage. And what I'd like to do is talk about why. To understand how the number of turns in a winding affects the voltage and the current, we're going to use our little test winding, our yellow one-loop winding that we used to estimate the amount of flux that was in the core. And if we look at it here, we have one turn, and interestingly enough, if I move these probes over here like that, and I didn't have an insulator on the wire, in the previous video I did this with the copper pipes, and one of the viewers was commenting that I was making a mistake because I was only measuring the voltage across half a loop, that half. Well, the bottom line is that in fact I was measuring the voltage across a whole loop because the rest of the loop is made up by the leads of the voltmeter completing the loop. So it actually turns out that it is virtually impossible to measure the voltage on half a loop, unless you could somehow do it by putting the leads of your voltmeter through a wormhole or something like that. I don't have a wormhole at my disposal. Anyway, there's our 0.2 volts. That is the voltage that this amount of flux generates for one turn. And you could imagine that if we had a certain load attached, and let's just pretend that we had a load that draws 1 amps at 0.2 volts, we would be generating about 1 times 0.2 equals 0.2 watts of power into that load. Now, what happens if we add one more turn to our loop? Or our winding, I should say. Well, here we go. Surprise, surprise, I connect it up. We have 0.4 volts. Not a big surprise at all. But now imagine with 0.4 volts, we want to draw the same amount of power as we originally did. Well, because we have twice the voltage, we would only need about exactly half the current. So we would only get half the current flowing through these wires. Well, here's the interesting thing is, we said we were dealing with 1 amp before to make things easy. Now we have half an amp. Well, that half an amp goes into our core and out and around and goes into our core again. So what does the core see? The core sees 1 amp, 1/2 plus 1/2, because it really doesn't know that it's the same electrons that are going around for a second go. All it cares about is the total current flowing through the core. So that's what happens. It's essentially natural that as you double the number of windings, you only need half the current to have the same effect on the magnetic circuit in the core, and in turn that gets transferred to the primary. So there you go. It is really quite simple as to why you have twice the voltage and half the current if you double the number of windings. And that's where the most basic transformer equation comes from, namely it's essentially the number of windings on the primary determining the primary voltage, the number of windings on the secondary determining the secondary voltage, and it's the proportion of the two that decides whether the transformer is a step-up or step-down transformer. Now, that's all good and well, but what we should do is we should look at some real transformers now. So the most common transformer cores are what you can see assembled here. We've been using a toroidal transformer core because it's easy for me to stick wires through the center for our experiments, but by far the most common cores are these EI cores, which are really the cheapest type of transformer to make. And what I did was I in fact cut the windings off the side of a transformer just like that so we could take a look at it. And here it is. This is the so-called EI core, and these are the windings from it. And you might be wondering why it's called an EI core. And it's called an EI core because it is made of laminations. And these laminations are in the form of E's, and then at the other end an I, which is just a strip of material. You might be wondering why there are laminations, and what I'm going to try and do is, I don't know if, yeah, I can get another lamination or two off so you can see it. There's the E, and can we get the I off? Yes, I think we can. It's kind of tricky, but there we go. That's the I. So here's our E, here's our I, and what they do is they have them alternating like this to form our core. Anyway, why do we have laminations? And we have laminations to prevent eddy currents, and I can show you that on this transformer. The way the core works is we have windings that go through the two holes in the core. The magnetic circuit is, if you want, this is the center of the core. The windings go around like that, and the magnetic field flows around here and around here. If we look at it on end, the windings go around like that, and primary and secondary are that way, so any circular loop like this will generate a voltage and potentially a current. Well, surprise, surprise, this piece of steel would allow a circular loop to form anywhere inside it and generate a current. That would be a complete waste. Well, that's called eddy currents. So what transformer manufacturers do is they use many laminations like this to try and make it impossible for current to flow in a loop, because what they try and do is insulate the spaces between each one of those layers to break up the loop. So that's the idea behind laminations. The other thing that the transformer manufacturers do is, you may or may not be able to see it, but it's a funny looking steel, and this is called silicon steel, that also has some properties that tend to reduce eddy currents, typically by making the resistance of this steel a little bit higher than regular steel. So eddy currents are in fact a source of loss for the transformer, as are hysteresis losses. Hysteresis is the result of this BH curve not being quite the same after you have reached a high level of magnetization. So if we apply some H field, in other words, some current, we move up the curve over here, then we reduce the current, and we don't actually follow the same path back. We move out here and only go down to 0 when the current is reversed. And then we continue on till we have a negative field, and once again, when we make the current less and less negative, we form this other essentially mirror image of the curve over here. It turns out that doing this consumes power in every AC cycle, and that's called the hysteresis losses. And so what manufacturers try and do is use a material that has these two paths as close together as possible so that energy is not lost. So the energy that's lost in the core is called, surprisingly enough, the core losses. Again, essentially the sum of the hysteresis and eddy current losses. And the size of that loss essentially depends on how big the core is, because typically you try and run the core just under the point of saturation. In other words, just under around 1 Tesla or so of magnetic flux density. The bigger the core, the more volume of core is subject to those losses, and the greater those losses are. So the bottom line is, you make the core bigger, you have more core losses. Now, the question you might ask is, why would you then make the core bigger? Well, there's only one reason to make the core that much bigger, and that is because you need more space for the windings. Well, why do you need more windings or bigger spaces for the windings? Well, usually it's for more current. If you need 500 turns of winding, as we did in our toroid, to operate nicely at 120 volts, well, if we're going to fit 500 turns in these spaces in our core, that pretty much tells us what the diameter of the wire that's going to be used has to be. And of course, remember, we need to not only accommodate the primary windings, but any secondary windings as well. And if we make that wire too fine, that limits the amount of current that can go through the wire. And it also means when current flows through the wire now has a greater resistance if it's very fine, and there is a amount of resistive loss from current flowing through the wire. And that is called the copper losses. So if you want to have a higher power transformer, you need more space for the windings because you need bigger diameter wires. What that means is you need to make the core bigger so that the hole in the core is big enough to accommodate the windings. That means there is more volume to the core, and that means there is more core loss, more eddy current and hysteresis losses. So for transformer designers, it's really a job of trying to pick the right compromise. You want to have the windings made of wire that is thick enough that you don't lose a vast amount of energy or create a vast amount of heat from the current flowing through those windings. And you also want to try and keep the core as small as you can to minimize the amount of energy that is lost in core losses. And depending on how the transformer is going to be used, you can move the compromise in one direction or the other. That's the basic idea behind transformers. I guess we could very quickly have a little bit of fun and see if we can pry apart this core to look at it. And look, we can. This was actually a high voltage transformer. So you can see that it has a lot of very, very fine windings. That would be the secondary, and I think over here, where would the primary be? The primary is, I think, right in the middle. It's this winding over here, and it's probably not visible on video, but these windings are clearly quite a bit thicker than these very many high voltage windings. In fact, there's so many windings it's hard to even see the individual wires on them. One other thing worth pointing out on this transformer is you'll notice there are big areas here and here with no windings. Normally this would all be filled, and I think it's because this is a very high voltage winding. I believe it was in the 5 or more kilovolt range. So what they've done is they've put insulation in here. So this core is probably way bigger than it would normally need to be for a transformer of whatever power it was designed for, because they had to devote so much space for insulation. So that's another compromise. Anyway, there you have it. Those are some of the compromises that transformer designers need to consider when coming up with all the wonderful transformers that we use in our electrical lives. That brings this video to an end. I hope you enjoyed it, and if you did, you might like my previous 2 videos. The first one was all about an electromagnetic chain, essentially a chain of transformer cores and 1-turn coils. And the other video was about magnetic saturation amplifiers and core memory, and it discussed saturation in a bit more detail than we did in this video. So take a look at those videos. The links should follow, and see you next time.